Welcome. Today we are going to solve 3 problems in the topic Bode plot. 63rd question. The figure below shows the Bode plot of the stable transfer function whose transfer function is given by g of s, and they have given the block diagram and they have given the plot, magnitude and phase plot for the transfer function g of s. So they asked, consider the negative unity feedback configuration with gain k in the feed forward path. The closed loop is stable for k less than k naught. The maximum value of k naught is. So they have asked to find the maximum value for the gain k for which the system remains stable. Coming to the solution, so just assumed t of s to be the open loop transfer function which is given by k into j of s. See, this is the open loop transfer function which is given by k into g of s. So we know that the gain margin, is minus 20 log based in magnitude of the open loop transfer function, which will give you the gain margin in decibels. And for the system to be stable, the gain margin must be greater than 1 or greater than 0 decibels. So for this, just substitute for the gain margin and it should be greater than 0 decibels, right? So after substituting, you will get a simplified equation, and you know that the gain margin for g of s is that you can find from this graph, because you have to find the phase crossover point, which is the point the phase plot intersects with the minus 180 degree line. That will give you the phase crossover point. So the corresponding magnitude will give you the gain margin. So this is the gain at the phase crossover frequency, which will give you the magnitude or the gain margin, which is 20 decibels. So just substitute for 20 log based in magnitude of g of s is 20 decibels at phase crossover frequency. So after simplifying, you will be getting k which is less than 0.1. So you must increase k 1 until you can increase the k until 0.1. So beyond that, if you increase, the system will be unstable. So that's why I have written here. So k must be less than k naught for the system to be stable. Coming to 65th question, consider a stable system with transfer function g of s where b1, b1 etc. b and a are the coefficients, real valued constants. The slope of the Bode log magnitude curve of g of s converges to minus 60 decibels per decade as omega goes to infinity. A possible pair of values for p and q are. So we have to find the possible value for p and q. So p is the number of zeros, q is the number of poles. So coming to we know that the slope of the plot converges at minus 60 dB per decade, which is given. So at the infinite angular frequency, the total slope is given by minus 60 dB per decade. We know that one pole will introduce minus 20 dB. So minus 20 dB per decade slope must be introduced by 3 poles. And also we don't have any positive slopes from which we can infer that the zeros there is no zeros. So from which we can tell the answer is p is equal to 0 and q is equal to 3. So the number of zeros is 0 and number of poles is 3. So coming to the last question, 66th question, the transfer function of a system has the form g of s, which is given by 10 into s plus 2 divided by s into s square plus 2s plus 40. At very high frequency, the Bode plot gain curve has a slope of. So they have asked to find the slope as the angular frequency goes to infinity. So from the transfer function, we can infer that there is the number of zeros is given by 1 and the number of poles is 1, and here it is a quadratic equation, right? So the order is 2. So 2 plus 1 will give you 3 poles. So 1 0 will introduce a positive 20 decibels per decade slope, and one pole will introduce minus 20 decibels per decade. So as omega tends to infinity, the total slope is given by plus 20, minus 20, minus 20, minus 20, because these are introduced by the poles and this is introduced by the zeros. So totally there is the slope is given by minus 40 decibels per decade and it is a negative. They have asked to find in terms of decibels per octave. We know that decibels per decade, 20 decibels per decade is nothing but 6 decibels per octave. So just by equating, you will get the slope as minus 12 decibels per octave. Thank you.